So this will cover topic 5, z-scores and the normal curve. This corresponds to chapter 5 in your textbook. So let's start with a quick reminder of how math works. When we talk about the absolute value of a number, we just mean the number regardless of its sign. So plus or minus 2. Here we can see the example on the PowerPoint. 2 equals both minus 2, this is 2, the absolute value 2 is denoted with 2 bars here, and 2, all right? If we see bar 7 bar, that's the absolute value of 7. This is negative 7, and that's a 7, right? And 7, all right? You can also put plus or minus. This little sign means plus or minus, so plus or minus 1, plus or minus any value, okay? It just means the positive and the negative form of it, the absolute value of a number. This is important because we will be talking about z-scores and numbers or values that are more extreme than the absolute value of a number, all right? So z-scores it refers to the distance a raw score is from the mean when measured in standard deviations. So z-scores are just any distribution or any score in a variable that has been standardized such that 1 is 1 standard deviation, 2 is 2, and so forth. Z-scores correspond directly to a location on the distribution. And what they do is they tell you the raw score's distance from the mean. So for example, if you have an 85% on an exam, a z-score could tell you how you did relative to the mean, okay? So we'll be using these equations quite a bit. So the z-score equation for a single score in a sample, for example, if you wanted to know your z-score on the first midterm, you would use this equation, which is just the raw score minus the mean for the sample of scores, right, divided by the sample standard deviation, okay? So this bit right here is this deviation. Deviation, as we learned in the last chapter, a deviation is just the difference between a score and the mean of the set of scores. The standard deviation, okay, it's just the average deviation from the mean, and it's the square root of the sum of the squared deviations. We did this last topic, right? Divided by the sample size, okay? Now, we can also calculate a z-score for a sample or a set of scores that we might want to compare to a population. And we'll get to this in a couple topics, right? This is very similar. It's just the mean of the sample mean minus the population mean divided by the population standard deviation. For this chapter, we're going to focus mostly for z-scores for a single score in a sample. All right. So for example, one student score in this class would be the z-score for a single score in a sample. And for the sample might be comparing this entire class to all the population of Bakersfield College Statistics B5 students, right? So let's walk through some examples of z-score for a single score, because this is what you're going to be using quite a bit. So for example, calculate z for a student who has a 90% when the mean is 75 and the standard deviation is 15. So remember, a z-score is just equal to the deviation of the score, which is the score minus the mean of all the scores, divided by the standard deviation, right? Standard deviation. So z for a student with 90 is 90 minus the mean, which is 75, divided by 15. So 90 minus 75 is 15, divided by 15 is 1. Okay, it's that easy. It's really pretty easy. How about the second one? Z for a student has a 60. So 60 minus 75 divided by 15. This is negative 15 over 15 equals to negative 1. Now, one of the biggest errors people make here is they forget the sign. So this is negative 1 and this is 1. Make sure you pay attention. The next one is calculate Z for a student who has a 75%. This would be 75 minus 75, which is 0 divided by 15. Remember, the Z score for someone who has the score equal to the mean of the sample will always be 0. All right. Let's walk through a few more. So now the mean grade is going to be 72, and the standard deviation is going to be 3. So let's start with Z for a student has 78. So 78 minus 72 divided by 3. So 3 equals 6 over 3 equals 2. Right? That's a pretty big Z score, as we will notice. That student has a score that is 2 standard deviations above the mean. So I want you to focus on something here. We can have means that look like they're pretty similar, but if the standard deviation is large, that means the spread, the variability of the scores in the sample is very large, right? So everybody is going to be pretty close to 75. Here we have a mean of 72 with a small standard deviation. That means someone with just a little bit higher score, 6 points higher in percentage points, is going to be a whole 2 standard deviations above the mean, right? So you really have to pay attention to standard deviations. All right, now let's do this one. 69 minus 72 over 3 equals negative 3 over 3, which equals negative 1. A pretty normal score. As we will see, 68% of all scores are within 1 standard deviation of the mean, right? Finally, Z for someone who has a 75. So 75 minus 72 over 3 equals 3 over 3 equals 1. Okay? So, pretty simple. So frequency distribution, just remember, a frequency distribution is just all the possible values, right? Okay, the distribution of all the possible scores in a sample. Okay, so we have frequency on the y-axis and the scores on the x-axis. Then we have the mean, which is right in the middle. Okay, and we're going to look a little bit more at that. First, I want to emphasize you can also go from z-score to the raw score, and you are going to have to do this occasionally. So let's remind you of how to do math. So our z equation is z equals x raw score minus the mean of x, okay, the mean of the sample, raw score minus the sample mean over the standard deviation, right? Okay, so to solve for the raw score x, you just multiply both sides by the standard deviation. These guys cancel out, right? Then we have to add the mean of x to both sides, right? So right now we have standard deviation of x times z equals x minus the mean of x. So now we just have to add the mean of x to both sides. And this one cancels out, and we get mean of x plus the standard deviation of x times z. Okay, we could put parentheses around here if we wanted to, but we don't need to, equals the raw score. Okay, so refer to this PowerPoint if you forget how to solve for x. All right, moving on to the z distribution. All it is a standardized distribution, and it's produced by transforming all the raw scores in the data to z-scores. It's going to have the exact same shape as the raw score distribution, okay? So if we look at this, if we have a standard deviation of 10, okay, the mean is 60, which the mean always is a z of 0, right? The mean of a z distribution. is 0. Okay, so we take Binky, who has a raw score of 65, 65 minus 60, which is the mean, divided by 10 equals 5 over 10, which equals 1/2. Look, right here, 1/2, Z of 0.5, right? Biff, who has a 90, that's 3 standard deviations above the mean. If a standard deviation is 6, right? 90 minus 6 is 10, right? 90 minus 60 is 30 divided by 10, 3, right? It's going to have exact same shape. All right. So simple rules, the Z distribution has the same shape as the raw score distribution. The mean of any Z distribution is 0, and the standard deviation is always 1. And here we can see it again. This one is from your textbook. We can see that we can convert 2 different sets of scores into Z, right? They're going to have the same shape of the original distribution. They're just going to be standardized. So we've talked about the standard normal curve before. This is the theoretical perfect normal Z distribution that serves as a model for any approximately normal Z. The total area under the standard normal curve is 1. In fact, the total area under any curve is 1, right? Any probability distribution. We can compute the relative frequency by just using the proportion of the total area under the curve. The relative frequency at any Z will be the same on all normal Z distributions, all Z distributions. So let's have a look. So remember, I just said how 68%, it's actually 68.26. But 68% of all scores in a normal distribution are within 1 standard deviation of the mean, right? So from -1Z to +1Z, all right? 95% of scores are within 2 standard deviations of the mean. Oop, that's a minus. Let's see. -2. All right. So when you're calculating your Z score, for example, if I ask you to do that and you calculate a Z of 10 or -5, your calculations are probably wrong because most scores are within 2 standard deviations of the mean. Now, the shape of the distribution can be different. There are many different normal distributions, right? So it could be that the standard deviation is very small, right? Here we have a standard deviation of 4, in which case we're going to have a distribution that is narrow. It's high, narrow, not very spread out, but we're still going to have 68% of the scores within 1 standard deviation. Here we have another example where our standard deviation is 7, so a bit bigger. Okay, the distribution is a bit spread out, but we still have 68% within 1 standard deviation, and C is even more spread out. So our variability is greater, but it's still normal. So we have 68% of all scores within 1 standard deviation of the mean. Here are the proportions for the total area. Okay, this is, as you can see, it's actually 0.6826. And if we wanted to get the proportion of all the scores within 2 standard deviations of the mean, we would add up all of these guys, right? And we're going to get back to this later, right? If we wanted to get the proportion of scores more extreme than 3 standard deviations from the mean, we'd add up these ones and these ones. More extreme than just means further away than a certain given Z score. All right. So for example, 0.3813 is the proportion of the scores between 0 and 1 standard deviation above the mean, and 0.3413 is the proportion of the scores between 0 and 1 standard deviation below the mean. So that total proportion is 0.6826, or 68.26% of all scores that lie within 1 standard deviation of the mean in a normal distribution. Okay, let's stop this recording and start.